This morning we learned about light. We learned about light intensity, composition, photo period, things like that. So what I'm trying to do now is I'm going to come up with some activities with these tutorials. And when you do these activities, those concepts will, you will pretty much remember that forever. So that's the plan, okay? So today's tutorial is probably going to be light. It's not going to be that complicated, but some of them might get a little bit more complicated. Please come. So that's what we're going to do. Um, did you see people still walking? No, they're all not. Okay. I don't want to go too far and then a bunch of people walk in, so we have to repeat that. Um, so I checked with Dr. Singh, and he's going to get you these PDFs. Maybe in a couple of days. They're waiting for one more faculty member to add some more lecture content. So you will have these packets with you before that. But for today, you have to look into the main screen and do these activities. Okay. Take your time. There is some simple math calculations, but then take your time and we can discuss one-on-one also. If you have questions, that's the meaning of tutorials. You got 2 hours, right? We can discuss, we can chat, and then maybe if you all finish early these tutorials, and if you have some time towards the end of the class, what we can do is we can discuss any other topic. Okay, if you come up with, okay, I want to know about this, okay, so we can sit down and chat. All right, so I also want to provide some additional information to you. Topics can be related to how does a student life in the United States, how do how do students do that, how do they get there, what's their path, what are the jobs that are there in this field, any kind of question related to science, education, things like that, we can definitely chat, right? Industry also, if you are from business, if you are from a startup company, you can bring up some of examples from there, and we can talk about that as well. All right, that's it. Let's start with the first tutorial. The tutorial is on light intensity and composition. I need to kind of, I think it is touch screen, so yeah. So there are 9 of them, okay? There are 9 of them, and let's go to tutorial 1 right here. So I have, my intention when I put these tutorials was that you'll have this packet with you so you can read it, and so I can simply go over, but today we have to do on the screen, right? Okay, so this tutorial is light intensity composition as I described, and I have some fundamental information up here. This is what you learned this morning in the class. We use, what I probably did not mention was, I said that there are sensors, right? We used to measure light intensity or composition, we have sensors, okay? I could not bring those sensors with me from the US because of the customs issues I may run into, so I was advised not to bring those sensors. I wish I brought them and showed you those sensors, but we're going to try and learn as much as possible about those sensors. So remember light intensity. Who can define light intensity for me from the morning class? Let's try that. One of you define light intensity. Okay, go ahead.
So it is the number of photons falling on a 1 meter square surface in 1 second.
And the units are?
The units are micromole per meter square per second.
Per second, right? Everybody agree with that? Everybody make sure you understand that, right? So how do you measure that? We use a sensor called quantum sensor. Okay, a quantum sensor is used to measure light intensity. The quantum sensor measures the photons falling on a unit area, meter square in this case, per second. But then you have to ask this question. You also learned about composition this morning. So what photons are being measured by a quantum sensor? The quantum sensors generally measure photons in the range of 400 to 700 nanometers. Okay, they don't measure the photons in outside of the range. But there are companies that sell quantum sensors that measure light falling of the photons in slightly outside the 400 700 nanometers. There are quantum sensors, what we call UV sensors, that they measure only UV light, ultraviolet light. There are sensors that also measure up to 750 nanometers, infrared, far red light, sorry. But let's focus on a quantum sensor. The classical quantum sensor measures photons between 400 to 700 nanometers. Only those photons. The other photons are not captured by the quantum sensor. Okay. How many of them are falling in 1 unit area per second? Right. Now, that is intensity, but before you do this activity 1, I want to describe about another unit called lumen or lux. They also call foot candles. These are some of the units people used to use to measure light many years back. But we don't use lumen or lux anymore, simply because those measurements, those units, lumen, lux, or foot candles, they are meant for photographic purposes. The camera professionals, they use those. These are more related to images or the human vision. Okay, these units put more weight on green light. Now, why green light? Because our human eye, the human eyes, please come in. Human eye has a particular pigment. We call this pigment as rhodopsin, and this pigment is very sensitive to green light. So we see, you see, for example, this white light that you're seeing up there, that has red, green, and blue, all three colors. When you combine red, green, and blue, you get white color. Okay, you can try that at your home. Take blue paint, red paint, and green paint, combine them in equal proportions, that becomes white color. Okay, so that's why these lamps are emitting white color. However, if you actually measure the composition, you will most likely see there is a lot of green light in that fixture. And the reason why they put green light, because this is an office lighting. This is what we use inside rooms like this and where people sit. So they put a lot of green light because human eye is sensitive to green light. It detects green light very well. And so that's why we see, even though the light is so low, we see it as a bright light for us. Okay? But for plants, it's not the case. If you look at plants, plants absorb light, right? Do you know what pigment absorbs light? Not phytochrome. Phytochrome is a different pigment. Chlorophyll. Chlorophyll is inside chloroplast, right? Chlorophyll. And chlorophyll absorbs two colors. Do you know what those colors are? Red and blue. Those are the two colors chlorophyll absorbs. Okay? And there is a good reason for that. I think there is an evolutionary reason why plant chlorophyll is more sensitive to red and blue, whereas the bacteria which evolved before plants, they were photosynthesizing too. Some of the bacteria in oceans, cyanobacteria, they used to photosynthesize and they were absorbing green light. So plants don't want to compete with bacteria, so they started developing pigments that absorb red and blue, not the green, mostly, right? Now keep in mind, when I say red and blue, plants absorb red and blue, plants also absorb green light, by the way. Okay, so let's talk about that. It's a slightly different concept, but you need to know this. If you look at all those three colors, red, green, and blue, which are used in photosynthesis by plants, 96% of blue light is absorbed by plants. Most of the blue light, 96%. About 90% of red light is absorbed. But when it comes to green light, only 70% is absorbed. 30% is reflected back. That's why plants look green in color. The reason why this cap is green in color, because this cap, this material, is reflecting green light. That's how we see the color of this cap. Okay, what you see is what is being reflected from an object. Plants absorb only 70% light and reflect almost 30% green light. They absorb 70% green light, but they reflect 30%. Compare that green light reflectance with red and blue. Blue is only 4% reflected. Red is maybe 9%, but green, a lot of green is reflected. And that's why plants' leaves look green in color. Okay? So keep in mind, plants do absorb green light, 70% of green light. So in other words, if you give 100 micromoles of green light, they absorb 70 micromoles and probably approximately 30 micromoles are reflected back. Okay? But they reflect more of the green light and that's why they look green in color. But after the green light is absorbed by the chlorophyll, green light is more efficient than blue light in terms of photosynthesis, simply because the energy of green light is in between blue and red. So red is of course the best, but then next comes green and afterwards is blue. Okay, you have to remember that. It's all energy dependent. So, so going back, we use a quantum sensor, but unfortunately I don't have a quantum sensor with you. Is there an internet on this screen that I can access web? Do you know? Yeah, but not now, but I'll ask you later on. But we can probably pull up some images and I'll show them how a quantum sensor looks.
So it might be available in the hydrometeorology observatory also.
Possible, but we may take a look at it. I'll ask, I do not know. I'll probably check with Dr. Ashutosh Singh and see if they have. But I'll show you some pictures. It's a very simple unit, and I'll also explain a little bit about how it works later on after the activity is done. Maybe that's what we'll do. If you've all finished the activities quicker, we'll talk about those sensors, the technology piece, how the sensors actually work, and what are the important things you got to keep in mind when you take these measurements. Okay, and I'll pull some pictures from online web, and then I can show you that. But because we don't have those quantum sensors for this activity, I want you to download on your phones if you have phones. If you don't have phones, work with your friend who has a phone. But there are a lot of light meter apps. Okay, they're free apps. I just downloaded while I was sitting there. I went on to Play Store because I have an Android phone. I went on Play Store and I found something called Light Meter. It looks like a light bulb. See if you can find this one. This app, so it's this basically it looks like this, a light meter, right? Light meter. Okay, just looks like that, a light meter. Okay, see if you can download it on your Play Store or whatever you're using a phone. It looks like a yellow color thing. Let's see if you can download the free app. Okay, light meter. You see that? Light meter. I'll get you to also something like that. It looks like a yellow color bulb. Yeah, light meter. See if you can find that app. Just download it. It's a small app, and then afterwards you can delete it if you don't want it to keep on your phones. But for this purpose, we'll use this light meter app. Keep in mind, this light meter is measuring in lux or lumens. So it may give you a number, but that number is correlated with quantum sensors measurement. But keep in mind that that number is heavily kind of skewed towards green light. Okay, but for this purpose it's okay, because the purpose is not about the sensor. The purpose of this is to kind of show you, to compare light intensities in different locations. Okay, just let me know when you all downloaded that. It's easy, you can just download that app. Okay, so originally what I was trying to do in this particular activity 1 is to kind of look at the transmission. Okay, so you have a greenhouse and light is coming through the greenhouse. You will learn about greenhouse shape and design, how they have influenced light transmission later on. But what is important to know is not all of that light gets into the greenhouse. Okay, some of the light is reflected back, and some of the light is diffused out to different sections of the greenhouse. So a critical thing about greenhouse is to maximize light transmission, right? The glazing material, polyethylene or glass or polycarbonate, whatever you use, that material should allow most of the light to get inside, so plants can use it. But what you will find in a greenhouse is that light transmission is going to be highly variable. Okay, so we think that when I say greenhouse, wow, it's a protected system, it's all uniform. No, it is not. It is not going to be uniform. Okay, so what I originally wanted was to actually take this light meter to a greenhouse, measure the intensity outside in the sun and also inside the greenhouse at different locations, and kind of map out what we call a heat map, something like that, map how much light intensity is there in different sections, and from that kind of calculate percentage of transmission. Okay, your goal should be to make that transmission as uniform as possible. Otherwise, what happens is if the light transmission is not uniform, some spots will get more light, some spots won't get sufficient light. Okay, and wherever there is more light, the plants will grow bigger, and other parts, when there is less light, the plants will not grow there. So you will end up with a crop that is not uniform, big, small plants, and that's not good. It will reduce your profits. You want a very uniform crop. The uniformity itself can increase the yields by 10-15%. So you want to make sure that the crop is uniform. And for one of the major factors that are affecting crop uniformity is light transmission. And therefore it is affected by, of course, by the glazing material. So in order to do that, you need to measure how much variability is there. Always keep in mind, as a scientist, data is powerful. Don't go by assumptions. Don't go by somebody said something. Validate yourself. How do you validate something yourself? You collect your own data. Having the data in your hand is actually, more useful than simply believing in what somebody said. Okay. So what we'll do is, because you arrived a little bit late, I just ask everybody to download an app on their phone, and I'll open it up. This is the app. So if you can download that app. So what I want you to do is, um, take your phones. So the first activity is about, so I'm going to, you can read this activity, measure light intensity using your phone outside, okay? Outside in an open area. See, you want to make sure that you're not being shaded by a building or a plant or anything, just in an open area. Measure the intensity in lumens. That's all right, take your time, no worries. But measure the intensity outside, okay? Just go to an open area, measure the sunlight intensity. All right? Let me see. You got it? So please show her also. Did you find this one? No, it just looks like that. Light meter. Alternative will also work. If you can find something that measures light, that's okay. You don't have to stick to this one. If you find something similar like a light meter, yeah, you can use it, okay? But I want you to take your phone. For example, if I click this light meter, and it takes a minute depending on the speed, and it's measuring me a number, isn't it? It's giving you a number, and as I closer to the the light, you will see the number goes up to 1100, 1200. But I come away from that, it goes down to 400. So it's measuring, not it is not measuring the photons of red, green, and blue. It's not intensity, but it is related to that. Okay. The ideal way to do this activity is to give you a quantum sensor and ask you to measure outside and in a greenhouse. Unfortunately, we don't have a quantum sensor. Yeah, that's okay too. You can try that. Lux meter too. Unfortunately, we don't have the quantum sensor with us, and also we don't have a greenhouse with us, right? So we have to do something different. But the concept is important. So I want you to get an idea about what we are actually doing, and then you can repeat that wherever you go back, and if you have a greenhouse, you repeat the same thing. Now again, keep in mind what you're measuring is lux, not micromoles per meter square per second, but this is related to micromoles per meter square per second with some linear relationship, okay? So in this activity, in the greenhouse, measure the light in 10 different locations. So we don't have a greenhouse. So what do? Well, what we can do is, just to do this, why don't you go outside, record the values outside, whatever that number is, but don't measure it one location, because it's always a random number. Measure in multiple locations outside too, maybe 4 or 5 locations, but make sure that it's not shaded, it's fully sun, open to sky, and record those 5 or 6 numbers in a piece of paper. Come inside. Let's consider that this is a greenhouse, okay? This is not, but we're going to assume that this place is a greenhouse, and I want you to pick maybe 10 locations in this room, and then go there and make a measurement. But keep in mind, I want you to make the measurement outside and also inside at the same height. Okay, if you're going to measure at this height, okay, I don't want to go to that corner and measure that height. Right there, you are creating a variable, confounding factor. Okay, but make sure that you are on par, I mean approximately the same height. Get 10 measurements, okay, record the data, and then come back to your tables. Then we'll start making some calculations, okay? Just go around outside, make some 5 measurements outside, and then come back, randomly select. Let's see how uniform the light is inside this, and then also see how much. And it's not transmission, but I'll get you, it'll at least give you an idea on what we can do. Okay? The speed, temperature, ISO. No, just the lux number. We want that lux number. I don't know why that's not showing up. So you couldn't find this app on your phone. See, this gives you a number, nice number like this. Okay. One. Actually, iPhone may. Okay, let's see what you're getting here. You're getting temperature in Kelvin. Okay, that's not what we want. Um, there's no other app. Let's see what apps you have. So no, you type light meter. You type light master, That's why probably you're not seeing it.
Light meter. It is okay, sir.
Okay, now click that one. Let's see what apps can you find. Um, let's see here. So is this what you downloaded?
It is 200, 400.
Oh, is it showing a number?
Yeah.
Can you take it closer and see if that number goes up?
Yes, sir, 100.
As you get closer to the light, it should increase, right? Do you get it? This is that's not what. No, that's giving you something else. That's why I'm worried about it. What do you see at that height? What? How much of the light do you see there?
Let's check the another app.
Yeah, I think that's better. There are several apps. I know why. See, I have a light meter app here. There is another one called another light meter here. So let's see if we can find something that is better for you. So is this what you downloaded?
No.
Let's try that luck.
Photo light meter. ये open किया था.
Okay, all right. Then let's try something else. Do you have what is this AI?
Light meter.
The same one?
Yeah. No, it is AI Lux
Let's
light meter.
let's try that if that shows the numbers for you.
This one is advanced. Yes, sir. Lux light meter pro.
That may ask you to pay when it's. Oh no, no, don't pay. There are a lot of free things. That's why I want to. Huh. Yeah, you went and voted. Yeah, it's showing you numbers. Sorry? It will fluctuate. It will fluctuate. A light is highly fluctuating. So take your best guess in that range. A best guess. So it's like 230. Oh, it's changing a lot because my hand is closing it. But if you place it somewhere where there's no obstruction, 490, 480, 490. So it's in that range, right? 485, something like that. Okay. You got these numbers outside. So you see how high they are, right? So that's good. Now take that same meter and randomly select 10 locations in this room, but at the same height, and record those numbers also. Okay? On this page of
Sir,
it.
this is paid one. 3 days free trial.
You have to pay for that.
Okay.
Why don't you do this? Why don't you use my phone?
Yeah.
Why don't you both take my phone and make the measurement so you collect the data, and why don't you combine both of you? If it locks, I'll open it for you. But as long as you do something like that, it won't lock for you. So why don't you take some measurements together, collect them, and then we can come back and we can do some math inside it. Yeah. Did you get your app on you? You have some numbers already. Oh, you're sharing. So you're going to go back again and collect some data. Oh, so you're sharing the work. You don't want to work too much. Reduce it 50%. Okay. So make sure that you measure the same height, even inside, also outside. Okay. But 10 locations. On 2nd, August 2nd, I think you're visiting a greenhouse. I'm pretty sure you're going to a greenhouse. So you can do the same measurements there with your phone app, okay? Unfortunately, I won't be available on that day to accompany you, but you can try that, okay? So what we want to now do is we want to first do some calculations. What we want to do is called percentage of light transmission. It's a very simple calculation, transmission percentage. So what I want you to do is, you see the formula there, transmission, it's always measured in percentage, okay? It is 100 times greenhouse light intensity, it's a spelling typo there, Whatever you measured in this room is greenhouse light intensity, and what you measured outside is the outside light intensity. In real world, you have to measure inside a greenhouse. Unfortunately, we're not doing it. But at least you will now know the procedure. Okay, you have a phone app. It's not exactly a quantum sensor, but at least something that will tell you how much light is there. But then now, when you divide outside intensity by greenhouse intensity by outside intensity, you get some sort of percentage transmission. Okay, here the transmission is 0% because the roof is not going to transmit any outside light, but in a greenhouse you get some light through, right? That's what you're trying to calculate, but the formula is same. The numbers, the percentage you're calculating may not make total sense because this is not a greenhouse, but that's how we calculate percentage intensity transmission. Sorry, you will also notice that in this case, the inside light, what is that number? Approximate. What is the average of the numbers you got inside?
60, 70, 80.
But that was outside, isn't it? What about inside? About 80? 280. Okay. Now keep in mind, if I measure right under the light, okay, at this height I get 500. I just go a little away, it can increase to, well, in this case it's pretty uniform. It is uniform. But what I want to tell you is, I think he brought up the point, every sensor is different. Okay, this is a cheap app that what you need to make sure is that you don't want to compare your number with your friend's number because they have a different phone, a different app. But to keep your comparison apples to apples, meaning you are making proper comparison, you have to calculate the transmission. Now, when you do the transmission calculation, those percentages probably will be closer amongst all of you. You may have a phone that gives you always a higher number, or you may have a phone that gives you always a lower number, but it is going to give a higher number or a lower number for both numerator and denominator, so that kind of cancels out. So your percent transmission most likely will be similar across everybody. Okay, again, keep in mind that percent transmission doesn't mean anything because there is no transmission in this room. What you're getting is through artificial light. Okay, but it's probably not even 10% in your case when you do that, right? However, if you are in a greenhouse, and if let's say it's a polyethylene greenhouse, it's a plastic covered on that one, okay, and that plastic is fairly new, you should at least see 75% transmission. Okay, the moment that transmission starts going down, it's time to change the plastic. That's why it is so important. So we expect that, it is as high as 85%. I've seen some of the polythene that goes up to 83 to 85%. But what happens is, with this polythene, they add a lot of additives. They provide, they add chemicals to polythene to protect the polythene from UV light. Sometimes anti-fog chemicals are added. Sometimes infrared reflecting chemicals are added. When all these chemicals are added to polythene, its transmission goes down. But usually polythene about 83 to 85%. So on the first year, if you're a greenhouse grower and you put a polythene and you measure the transmission, you get something like 80%. 1 or 2 years later, you're measuring 70%. That tells you that it's time, that polythene is old, is no more of use. It's lowering the intensity of light. It's going to cost you more because the plants are not going to grow well. It's better to replace that with a new polyethylene. Okay, but usually you will see that the transmission under polythene is close to 80%, 75 to 80%. If it is glass, you will see close to 90%. What means is, when you're measuring, let's say 20,000 outside, inside you measure 90% of that, meaning 18,000 micromoles. Okay, glass has high transmission than polyethylene. Polycarbonate in between glass and polyethylene in terms of transmission. Okay, but you need to measure transmission for two reasons. You need to know how uniform is your greenhouse in terms of lighting. You want to make sure that everything is uniform. If not, there is some problem with some structure. So if you notice that some patches are always getting low light, once you know that, either you can avoid growing anything in that patch, or you want to grow plants that need less light. Okay, some species require less light. For example, let's say you are doing a business where you are growing tomatoes and also leafy greens. Okay, Leafy greens in general require less light compared to tomato. So once you know that, oh, there is a transmission problem in that area, let's grow, in that case, leafy greens there. And wherever there's high transmission, let's grow crops like tomatoes, which require more light. Okay, so that's how you can use that information. And also you can use that information to replace the roofing material, glazing material. When it gets old, transmission goes down. That's another reason. But I want you to do the same thing when you go to the greenhouse. Measure the intensity outside before you get into the greenhouse with your phones. Just 1 or 2 numbers. Go into the greenhouse and measure few places. You will immediately see that two things will happen. The light numbers that you're measuring will be fluctuating a lot. That's the real deal. Photons are falling, and they are falling randomly, so it's a highly fluctuating number. A little bit increase in height of your phone will make a big change in the number. So make sure you'll observe that. But as you are walking in the greenhouse, different locations, keep recording the data. And you come back and do the same calculations, as this activity at some other point. Okay, so that's how you calculate transmission. Greenhouse intensity by outside intensity. It's a very simple, and multiply that by 100 to get the percentage. But that transmission gives you a one single average value. In research, always keep this in mind, people go with averages. So let's say a simple trial, okay, you are comparing two fertilizers, A and B fertilizers, and you get yield for A and you get yield for B, and you look at the average yield for A and average yield for B from different repetitions or replications, and then you compare the average. That's okay, but it's also very important to know how much variation is there. A lot of people don't look at variability, but that variability is telling something. It's highly important economically. So I may have an average here for A and an average value here, a little bit lower for B. But if this is highly variable, meaning the error bars are big, they are not different statistically. When you run statistical analysis, there is more variability, even though the means are different, they may not be statistically different because there is a lot of variability in that measurement. So you have to pay attention to variability. Many ways you can calculate variability, and one simple method is standard deviation. In Microsoft Excel, there is a simple formula. You select everything and say equals to STDEV, standard deviation of the data, and throws the value for you. Okay, and that's what it is. Basically, standard deviation is calculated as xi minus mu by n minus 1. So xi minus mu whole square by n minus 1. What is xi is, let's say you measured a value here, light intensity, another value here, and another value here. You get the average of these three. That is mu. Mu is the average of these three values. Xi is this value, is x1, x2, x3. So for x1, you go take this value and subtract it from mean, square it, divided by, in this case, I have taken 3 measurements. So n is 3. 3 minus 1 is 2. As simple as that. So here is x1 minus mu, here is x2 minus mu, here is x3 minus mu. Whatever the difference, add all those 3 things and then divide by n minus 1 to get the standard deviation. If you don't want to do all the math, go to Microsoft Excel. Type your x1, x2, x3 values. Select all 3 and say STDEV equals to STDEV of that range, and it gives a standard deviation. So you get standard deviation. So now you have a mean value, you have a standard deviation value, and I'm going to now talk about a particular measurement. Some of you may have done that in your math classes. It's called coefficient of variation, CVs, coefficient of variation. If CVs are more than 25%, then whatever you are collecting, that is highly variable. That may be a problematic situation. In research or in experimentation or in production, whatever it is, your CV should be tighter. The variation should be less. When you measure light intensity at different locations, they should be tight. That tells you how uniform your data is. That tells you how uniform the light transmission is. So I want you to calculate CV, and there is a simple formula for CV. It's standard deviation over mean times 100. That's it. Okay? You calculate standard deviation, you calculate mean, and CV gives you that. And if you are finding that it is 35-40% in that greenhouse, that means the greenhouse has a problem. It's got a light transmission problem, highly variable. We can tolerate up to 30%, but if you are seeing CVs of 50-60%, I think it's time they do something. It's highly non-uniform data. Okay, ununiform data. So uniformity is the key thing, and light transmission should be uniform, and this is the measurement we want to see end of the day. The CVs should be low, 25, 20%, pretty good greenhouse. Light is uniform inside. So now we have come to a measurement, a calculation that will tell us, is that light transmission uniform or not? Light transmission is easy. You calculate by dividing, outside light intensity, and once you know outside light intensity and greenhouse light, you can calculate transmission. But the question is it uniform or not? And for that we need a measurement, and that's what the CV is. Okay. So what I really want you to do is, I thought we could do sort of like a mathematical calculation. But when you go to the greenhouse, prepare a table like this. I hope that by the time you'll get your tutorials packet also with you. See here, location 1 to 10, right? That's exactly what you did here, right? Do the same thing in the greenhouse, 1 to 10. And at each location, measure the intensity in, well, it says micromoles, but you're not going to get micromoles, right? In this case, you have to use your lux meter. So put those numbers here, okay? And then you see here outside light intensity. Measure it outside before you go into the greenhouse, 2 or 3 locations, and put an average and calculate transmission percentage at different locations. Okay. After that, you calculate the mean, standard deviation, and coefficient of variation, and come back and know in sometime in August, 5th or 6th or 7th. Let's see how variable that greenhouse is transmitting light. Does it make sense? How to do this simple light transmission calculation? Most importantly, not just light transmission. From that data, how can you say if the greenhouse is uniform in terms of light transmission or not? Calculate the CVs, coefficient of variation. Okay, but you got to do at 10 different locations. There are some important things to keep in mind. You have to keep your phone at the same height. A little bit of lowering or highering will change the numbers. So that's not the real issue there. Then the problem is you are causing confounding effects by changing the height. So make sure that you measure the same height, but at random locations, different locations. Okay, and then fill up this table at some other point of time. Okay. So that's the transmission, first fundamental simple thing. Every grower, every person should do. Unless their light is uniform inside the greenhouse, it makes no sense. They are creating a problem otherwise. Okay. All right. That's the first activity. This one I think you can do right here. Remember, we talked this morning about energy concept, right? Each photon carries some energy, right? And there was an equation. What was the equation? Can anybody tell me that energy equation? Right? E is equal to hc by lambda, right? So that's what we want to do. And I want you to calculate the energy of photons of 385 nanometers, 450 nanometers, 550 and 620 nanometers using that equation. I gave all the information to you. But the most important thing is, you see here, calculate the energy of photons with the following wavelengths and convert the values into electron volts, EVs. 1 joule is equals to these many electron volts. So it's just a little math problem. You will need your probably calculator on your phone. But I want you to get that. Once you do for 4, you will not forget that formula. Okay? Let's do that simple math. Hc by lambda, okay? You will get the energy in joules and then convert into electron volts. And I want to see how many electron volts are there in UV, 385 nanometers UV light. In the blue, in the green, and in the red bands. Okay. Take some time, maybe 10 minutes. Even if you're faster, that's good. 5 minutes. Let's see what EV values you're all getting. Hc by lambda. H is Planck's constant, and the value is right there. 6.63 times 10 power minus 34 joule seconds. C is the speed of light. 2.99 times 10 to the power of 8 meters per second. Okay. Minus 1 means per second. Right, and lambda is the wavelength, and that is given here in nanometers, but you have to convert it into meters. So read the information there. There is a lot of information there. So once you do for one, you will get it easy for the others. There are a lot of conversions in that calculation. Okay, do it independently, do it yourself. It's okay if you make a mistake, but we can correct it. So I want to mention one thing to all of you. Look at these units. For Planck's constant, the units are joule second. Okay, so that is H value, right? You take, let's not worry about the numbers, but let's look at the units first. So this is joule seconds, right? You take joule seconds and you multiply with C, H times C, right? Units of C is what? Meters per second. Here is joule second and here is meters per second. So what happens? The second gets cancelled, right? So you end up with what? Joule meter up to this point. Then now you divide by lambda, Hc by lambda. The lambda is in what? You want the lambda to be in meters. These are nanometers. You have to convert this into meters by multiplying by 10 power of minus 9. But then when you convert it, the lambda becomes meters. So joule meter by meter gives you joules. So the energy is measured in joules. Okay, so units kind of cancel out. You should get the values in joules and then you take that value and multiply with this to get in electron volts. Okay, simple math. Well, I want you to do all of these and then we'll compare the numbers amongst us. Okay, if you have finished all four, that's great. You should see a trend here, an increasing energy as you go from 385, I'm sorry, a decreasing energy as you go from 385 to 620. If you have a laptop, it's so easy. You just plug in those numbers into Excel and it'll give you, right? But also do it by hand so you will remember that. Is it making sense? Anybody is having a problem with calculations or the logic? This makes sense. It should be a simple thing. Has anyone finished all four? Okay, a few of you. Okay, just gives a few more minutes for others to finish, and then we'll compare the numbers amongst all of you. This for me? Oh, that's okay. Thank you. Who needs more time? Please raise your hands. If you need more time, please, it's okay if you need time. I just want to know how many people are still working on it. You finished all of you? All pretty close? You finished, right? Okay. They are working on it and you said you finished. How far are you? Getting close? You finished? How far are you? For 1? Okay. You don't want to go beyond that. Okay, that's all right. So 6 points, 10 to the minus 10, 2.99, 10 to the 8 by 3. This 385 is in nanometers. So 10 to the power of minus 9. Okay. So minus 9 and 8. So you have minus 1 here. Okay. So that becomes 38.5. Then this divided by this and 10 times 10 to the power of minus 34. And then this seems to be quite low. It should be something like 1.24, 2.03, something like that. I just don't know the answer exactly, but let's see what others have gotten. So who has finished the first one? 385. Okay, let's see your answers first. What was the number you got? 3.18. How about you? 3.23, but pretty close. See, that's what it is. So somewhere there, you got 3.18. So 3.2. Yeah. So,
3.21.
okay, but you got this number. This is a big number, right? Something went wrong there. 3 point, who got 3.2, 3.18? 3.2133. Okay, pretty close. Did you get the similar number? 3.2 for the 385 nanometers. Somewhere there's a mistake. Somewhere there's a mistake. Most of them are saying 3.2. I want at least one of you do the 620 nanometers, the lowest one, and tell me what is the number you got for that.
0.668.
0.68. Let's see what others have seen. You got 2? I think he's close. That's what I would expect it. Oh yeah, 1.99. See, something's going on. So it should be close to 2. Three 385 and 420, 620 at least, those two. So 3.2 to 2.0. That's that much difference, right? Check your math. If you're close, there's a small something you may have done. It's all about those minus indices. Sometimes they don't get cancelled well. You didn't get that still?
6.63 divided by 620.
What about
Multiplied by 6.247. There is only difference of 1 0. So it should be 0.66.
so 6.63 times 2.99? You forgot that 2.99? That's what it is. So how far are you?
Actually, we didn't multiply with that. We didn't convert
Yep.
it into ED.
Yep. So look at the electron volts. I said the red light is enough, right? And what are the numbers you're getting? Close to 2. 2 electron volts are enough for photosynthesis. Okay, if you can get close to that 1.8 to 2, I think 1.86 or something is the number that they predict. But red light 620 has the highest maximum photosynthetic efficiency simply because the energy is close to that 1.8 to 2. Okay, but UV on the other hand has much more energy, almost 50% more in this case. And when you hit the plants with so much of energy, the plants are getting stressed. Yeah, infrared. Yeah, what did you see? Far red, sorry. 1 point? Yeah. And as you go further down to microwaves and radio waves and TV waves, the energy goes down. Now, here is an interesting question for all of you. You know, a microwave ovens, yeah? Do you use in your homes, right? When you put water inside and turn on the microwave oven, what happens to water? It starts to boil. What does boiling means? It's getting energy and it's boiling. Will water boil in natural sunlight? I mean, if I put it under, let's say, red light or green light or blue light on top of water, will it boil? It won't boil. But it is boiling for the microwaves, which has got even small energy than blue light. Does it make sense? Because as you go down, the wavelength increases. As the wavelength is increasing, the energy is going down. But here I am saying that when you put water in a microwave, it boils, but water doesn't boil under a blue light, which has got more energy. So why is that? Do you catch my question? So let's say you take a water in a glass bowl, you put into a microwave, you turn on the microwave for 5 minutes. After 5 minutes, you'll see the water inside the microwave is boiling. Okay. If you look at this, the UV light has more energy, 3.2 something. Red has less energy than UV. So as the wavelength is increasing, the energy goes down. So they are inversely related, right? As the wavelength is increasing, the energy goes down. Microwaves are even a longer wavelength than red light, than infrared light too. So their energy should be less. But still you see water boiling inside a microwave, but not under simple blue light.
Vibrations, internal vibrations.
So multiple answers. So let's start with her and we'll get to you.
Vibrations.
Vibrations. What about your answer?
Like shorter wavelengths carries more energy per photon than compared to longer wavelengths.
Yeah, but microwaves have longer wavelengths.
But they like bounce back and forth, like they go in.
That's one reason, but what's basically happening is inside a microwave, your intensity goes up. You are hitting them with so many of them, and that's why the water starts eventually vibrating, and then it starts boiling. Okay, but again, just an example. All right, TV waves and radio waves. The wavelength of TV waves is like miles and kilometers, and that's why we use TV for propagation signals. That's why we watch television. Even in olden days, in 70s, when the TV stations used to come, where I used to live in Madras, there used to be a TV station. I used to live in a place where it was like 200 kilometers away from that place, but we still get the transmission to Madras. It's now Chennai, but I used to get because the TV waves are so long. Each wave itself is kilometers long, so it's easy to transmit signal through that. Okay, but in any case, but you get the picture now. You now know how to calculate energy of a particular photon. So why is this important? Let's say you are going to choose a specific light for your crop. You need to know the intensity, you have the composition, but also now you know the energy. And if you're thinking that it's got a lot more of UV and blue, that energy is going to cause problems. Okay. There is one more activity. It's about light composition now. Okay. Light composition. That's the last activity. Let's see if we can. Well, in fact, I had 7:30 also, but I didn't show that, but you did it, so that's good. Um, let's see, where am I? Okay. I thought I had 3 activities. What happened? Huh. I think we need to get some help. Let me see if I can find somebody. Can you help me with the? Well, it's not going. Is it the end? It's only showing 5 pages. It should be more than that.
So there must be any other video.
No. See. Tutorials. Sure, sure. Um, in the meantime, while they're pulling, I'm going to show you some companies that sell these sensors. Okay. Um, there are two companies that sell quantum sensors. They're like good ones. Okay, the first one is a lot expensive. It's about $450 each sensor is $450. So multiply that by 87 rupees, you can get the number for the price of that. That is the price in the United States. They may sell it even higher price when they bring that product from US to India, right? Because they have some additional costs, shipping and things like that. It's a quantum sensor. The company's name is Licor, L-I-C-O-R, Licor. Okay. Now I should not be advertising, but I am LICOR, Licor, but I'm not advertising for any specific company. Disclaimer, okay? I'm not saying one is better or the other, but these are the two companies that we in academia in the United States, we use it. So if you find another company in India or any other country that produces quantum sensors, they probably are equally as good as the companies I'm referring to, okay? So you can probably go online on your phones and check for licor.com, licor.com, and go to, I'm also doing it parallelly with you, so I know where to guide you. Depending on the speed of my internet. Huh. So when you get to Lycar, you'll see something like this in blue color, right? Click on those three bars and go to, let's say, light. See, once you click on the three bars, you'll go to light. Um, and then you start seeing sensors like this. Okay, this is a quantum sensor. Okay, I wish I could show it on that screen.
He might have the access to the screen.
Can you access?
So what it is then? LI.
COR. So I actually want to go to other pages. This is quite annoying. I want to go to page number 6. Can you put page number 6 for me, please?
This one, sir?
Yeah, this one. Could you please leave it there? And we'll get back to that. But let me finish this with them first. So that is a quantum sensor. Okay. That is how a sensor looks. Okay. You see that picture? I don't know whether I can. Can you pull internet on that? Do you know? Otherwise, it's okay. They can. I don't want to change this because we're going to go back to this. But can you just minimize this and open another web browser for me? Huh. How do you type there? Okay. Oh, you have to. Yeah, yeah. I see that. We go here and products and go to
That was all.
Ah. So this is how those quantum sensors look. You see now, they're about that size. They're about that size. You have to place them on a plate. You see that there is a plate there. It should be perfectly flat. And usually these are connected to a handheld unit device. So you place them on a floor or some standard bench or something, perfectly upright, not tilted at any angle. It should be perfectly upright. Then you get the numbers micromoles per meter square per second. That's what that is. Leica is. Okay. The other company, if you are interested, it produces also a real good quantum sensors. It's called Apogee, Apogee, apogee.com. And they have a range of quantum sensors, extended quantum sensors, full quantum sensors, whatever that is, original quantum sensors. That's another company. Now, the point I'm trying to say is, if you look at this car, see right here, how they measure intensity in a greenhouse. Right there is a small LiCAR unit. You have to place it in a greenhouse and it's continuously measuring. The power of the LiCAR is, or any other quantum sensor, even with apogees or any other quantum sensor, is that the most important thing is you notice that intensity changes rapidly, right? So you have to place the sensor in a location and you should be able to measure the data continuously, non-stop, every minute. So that way you can calculate DLI, daily light integral. Okay. So we normally connect these sensors to data loggers, and these data loggers kind of measure the light intensity, collect the data, and then also calculate how much total light has been received using that same formula, DLI formula. I told you this morning, they use the same formula and automatically calculate and tell you total amount of light received every day using these sensors. Some days you get 15, some days 5, some days 30 moles per meter square per day, it doesn't matter. But at least you know how much fluctuation is there. You know, that's the power of that. Okay. So this is one. Apogee also produces sensors. These are the two sensors we commonly buy in academics, but there are also many other companies. There are a lot of cheap sensors. I want you to remember that. A lot of companies on the web sell sensors. All these light sensors should be what we call cosine corrected, meaning they should measure sort of like a hemisphere, light coming from all, in sort of like a dome in a hemisphere to get the right value, but they don't do that. Some cheap companies so basically what is a light sensor? It's a photodiode. If you have heard about photodiodes, these are very similar things that they use. Have you seen these solar panels? Solar panels. Inside the solar panel, there are cells, and each cell is a photodiode. Light falls onto that photodiode and creates a current. Light energy is converted into an electrical energy, and that current is captured and saved, right? And then converted into other forms. Same concept here. It's a semiconductor. A photodiode is a semiconductor, okay? And what it's basically doing is, as the light falls onto that, it hits that photodiode, creates an electrical current, and that current is converted into intensity by a calibration factor. That's how the sensors work. Okay. But all of these sensors are photodiodes, and you can get a photodiode for tiny bits, like small tiny things are like cheap stuff. Few, maybe 20, 30 rupees, you can get a tiny photodiode. I don't know the exact number, but they're very cheap. Okay. So some companies simply put photodiodes and give you a number, but that's not an accurate number. By the way, what you measured here is probably doing the same thing. It's very inaccurate, but that's how. But you got to go for good quantum sensors. If you are serious into this business, you want to buy a good quantum sensor, which will cost you something. These are expensive, but they are also powerful. You can connect that to a continuous logging system, so you can see how much light these plants are receiving. Now you can also take that same LiCAR and measure your transmission percentages in your greenhouse. That way you know how much variability is there from location to location, but then you can probably afterwards place it in the center of the greenhouse and start measuring light intensity. Whenever you see the light levels are lower, like lower than 5 moles, something like that, you need to turn on artificial lights. Okay, that's how you do this. All right. So a couple of companies, they sell that.
Which model is the best in
FOG, like full spectrum quantum sensor is that?
Yeah, there's a full spectrum that gives you all of the numbers from 400, 700, or maybe also from 380. Well, that's 400, 700 is full spectrum. There is an extended quantum sensor, something like that, that covers I think far red and UV also. Okay. But again, like I said, I want to mention again the disclaimer. I'm not recommending a company versus another company, and I should not do that too. I'm just giving you a couple of examples. There may be companies in India that are producing high quality quantum sensors. Okay, I do not know that, and that's why I'm not referring to them. Okay.
Like, for example, these sensors are quite costly, and there will be a very high chance of someone stealing them as well if we put too many of them in a greenhouse or something.
There are a lot of expensive stuff in your greenhouse, not just these sensors,
How
right?
does people in India like manage with the traditional methods of intensity measurement? Like, I want
Well, if you are worried about people stealing things in your greenhouse, maybe you want to buy a handheld sensor, which is meaning a sensor and connected to a meter. You measure it wherever you want and put it in your office.
so that is also available from Lycos.
Yep. Yeah. Yeah. I think they cost about $1,100 or more than that with a handheld meter. But these are expensive units, sensors. Okay. Ideally, if I'm doing this course in the United States, we give students these sensors so that they take the sensors and go to greenhouse and measure in micromoles per meter square per second. I couldn't do that, and that's why I ask you to at least practice with a lumen or lux measurement. Okay, but just so you know, these are the right sensors. They measure between 400 700 nanometers only, and they are cosine corrected, meaning the numbers you get are very accurate. Again, there is a rule of thumb with any sensor. A sensor is only as good as its calibration is. Okay, so you buy a Leica sensor and you don't calibrate it for 5 years. Maybe it's an expensive sensor, but its calibration is totally off. So all you're getting are random numbers there, right? So you have to calibrate those sensors. There are direct and indirect ways, but that's a different story. Occasionally, you have to calibrate them once every, I would say, 2 or 3 years. Okay. But again, I want to go back. I'm not sure. Excuse me. Can you help me here? I want to go back to that code file uh, behind this web file. Oh, you press that, okay, and then go back. No. I want to close the web completely. Um, I don't want even this. I want to go to home, okay, and I know. So while she's pulling that, so the activity 3 is about DLI, daily light integral. Okay. So remember this morning you did some calculations on DLI, right? I gave you 100 micromoles per meter square per second, and then you calculated for 12-hour period how much DLI was that. I think the answer was something like 4 moles per meter square per day, something like that. So what we will do is now a similar example. So you'll remember that concept. I have a table here. You can see here on the first column you have hour, 1 a.m., 2, 3, 4, like that, all the way to, it should end at 20, yeah, 24 is right. So 24 hours, okay? And then you can see sunlight in the first column in micromoles, okay? The sunlight is, there is no sunlight in the morning between 1 o'clock and 5 o'clock. Sunlight starts to show up around 6 and then goes up higher in the afternoon and then becomes 0 again at night. But whenever there is no sunlight, we are adding artificial light. And we are adding only 125 micromoles constant artificial light. What I want you to do is, I want you to calculate the intensity integral for every hour and then add them all together to get the total DLI. Okay, so this is the light intensity coming from both sunlight and artificial light. Use the same formula that I gave you. DLI is, you take the intensity, multiply that with 3600 to get the total light per hour, right? Each row is per hour. So for each hour you calculate the total intensity by multiplying with 3600 and divide that by 1 followed by 6 zeros to get in moles. Then add all those 24 numbers and tell me total light intensity in a 24-hour period. Okay? if anybody has an Excel, it's very easy to plug and give the answers. If you brought your laptops or you want to bring your laptops, bring the laptops tomorrow. They might be useful. Let's see if you can do some math here. Um, the easiest way to do this is add these two, have another column, okay? That's the total intensity per second. Take that number, multiply by 3600, you get per hour. Divide by 1 followed by 6 zeros, you get moles per hour, moles per hour. Keep on adding all of that, and in the end you'll get the total. The smart way of doing this is each of you take one row, okay? Complete the calculation for each hour and then combine all of that. So you don't have to do 24 numbers, right? Maybe we can start from, I don't know, wherever you want. Hour 1, hour 2, hour 3, 4, 5, 6, 7, 8. I think we're less than 7, 8, 9. So whatever you want to do. So you don't have to do all 24 because it's the same repeated.
1 to 5 is same value, 0.45.
Exactly.
And 22 to 24 is
Will be also the same value. The remaining will change because sunlight is changing, right?
For 6 it is 0.504. For 7th it is 0.9.
Just do the addition for me. I want you to tell me how much moles are coming from artificial light. How many moles are coming from sunlight? 46 is the total. All of them. Yeah. 46 moles of light. There's a lot of light. Yeah, good. That's what you get normally in summer. In summer in this part of the world, in a greenhouse, you get that much light. But the point is, if you do for few numbers, then you understand how to calculate DLI. And again, keep in mind, I just added up these numbers, right? So somebody did the calculation, they got 46 moles, 45, 46 moles. Anybody can confirm that. Anyone else can confirm that. How is this going for you? Okay. Anyone finished the entire 24 hours? I know you finished, but anyone else then? He says 46 moles. I want you somebody to confirm that it is close. How could you do so fast? Yeah, how could you do so fast? Ah, there you go. See that? He has a laptop. But 46. So she did manually. So you can do that way. The bottom line is that 46 moles of light per day per meter square area. That's what this is giving you. So going back to your question, sir, you said I have people, they may steal things. You know what you got to do when you have a situation like that? You have to take that handheld unit, go every hour and measure for 1 minute or 1 second, whatever it is, record that number and do it over the day and do the same calculation to kind of at least get close to the average DLI you get. The other easy way is connect that sensor to a data logger and it will log the data for you, it will do the calculation for you. And then it does it every day for you. Okay, so that's the power of data loggers, and there is a chapter on data loggers towards the end I will talk about, but I just wanted to introduce you that term. Okay, but at the end of the day, the DLI concept, the energy concepts, right? Um, the transmission, the uniformity, they're very, very important. These are all tied to the lecture we talked this morning, right? We talked about the basics, but the stuff that you're doing is applied. If you are a researcher in a greenhouse, if you are working in a greenhouse, or you want to own your own greenhouse, you need these basic calculations. You need to know how much light you're getting in your greenhouses. Light is one of the fundamental factors that affect plant growth. Whether it is coming from sun or it's coming from an artificial source, you still need to know. For example, in this case, you are giving 46 moles. It's actually a lot of light. Plants, some plants like tomatoes and strawberries, they need about 25 moles, 20 to 25 moles. For leafy greens, you need less light. You can do with 10, 12 moles or 15 moles. Tiny seedlings, just 5 to 6 moles when they are in a propagation stage. Okay, if you are growing shade crops, tropical plants, in greenhouses like Dieffenbachia, aglaonemas, monsteras, philodendrons, they are shade plants. They grow under shade, so they don't need a lot of light. So unless you know how much light is there, you are not sure whether the plants are in the optimum environment or not. And how do you know how much light is there? You need a sensor. Bottom line, you have to buy a sensor. This is just a sort of like an example for you, but sensor is what you need to buy. Okay, about 12, 10 to 12. 12 would be ideal. 12 to 15 max. Okay, seedlings, leafy greens, tomatoes, peppers, strawberries, they need more and more light as you go in that line. Okay. Uh, so again, we have one more topic tomorrow on light. We're going to talk about artificial lighting, supplemental lighting, LED lighting, and a lot of other concepts tomorrow. That will close the light chapter. But because we got some time, let me ask you, was there anything that was not clear to you from the morning session, from the lectures? Or do you want to ask me more about anything related to light in general? This is your opportunity to ask. Okay.
Sir, it is any difference between the red flowering, yellow flowering, blue flowering, the light requirement?
So the question is, let's say you have flowers and there are different colors, yellow color flowers, white color flowers. Do they require different light qualities or composition, right? Again, the answer is no in general, because the light is related to photosynthesis. What we are talking about is about photosynthesis, and that's happening in the leaves. Although some photosynthesis may happen in the flowers, but that's insignificant. So in terms of leaves, whatever concepts I talked about, the intensity, composition, that's what matters. Okay. We have done research, and let me talk a little bit about the type of research we do and what we found uh, from our research related to light in greenhouse production, crop production. Um, One of the early research that we did was kind of to look at um, supplemental lighting, which is artificial light. We want to provide at night time. Okay, you can add supplemental lights during the daytime too, but at night time, I do not know how it operates here, but in the United States, in some places, uh, energy consumption goes down at night because people wants to sleep, so they turn off the lights. So there is not much of a demand for electricity. So the prices are different at night versus day sometimes. Okay, it's not the same price. Electricity price is not same throughout the day. So we wanted to see if you just apply the supplemental light. Again, the concept is total light per day. So we want to keep the total light per day same, but we want to give that supplemental light during the daytime versus nighttime, and see if there is any advantage to that. And we found that actually by giving supplemental light at night time and not at the day was actually as good as giving light during the daytime too. And but in doing so, the electricity energy costs were less for us. Um, we did a lot of research on light composition. One of the pictures I've showed you this morning was on the lettuce crop, right? I've done similar studies on marigolds. We've looked at how each wave bands, we had some 7 or 8 different types of LED lights that were giving blue, green, yellow, orange, just that light, okay? And we wanted to see how that affects plant growth. And it kind of confirms that photosynthetic curve I've shown you, where the red gives you the best and then everything drops after this. So that is also confirmed. We did that study. but more recently we are into using that light quality as a way to increase the nutritional quality of leafy greens. Okay, so in leafy greens you have vitamin A, beta carotene is a precursor of vitamin A. So in all the leafy greens you'll find vitamin A, but the levels are not high enough that they will meet the daily requirements for us. Okay, we have to eat certain amount of vitamins every day to be healthy. And so of course you can get vitamin A from carrots, but not everybody has access to carrots, right? And a lot of people in the United States eat salads which are leafy greens. So we wanted to see if we can actually increase those vitamins in leafy greens. uh, there are multiple ways of doing that. One way is to breed new varieties which has got higher amount of vitamin levels, but breeding is a slow process. It takes 10 years, sometimes 15 years to release a variety. So what we were thinking was, okay, what happens if you uh, expose these plants to different light qualities? So is there any specific light quality that increases nutritional quality, vitamins, anthocyanins, things like that? And we found that, um, and I kind of told you this morning, initially when we hit the plants with UV and blue light, the 385 and 450 nanometers, they had higher levels of beta carotene and anthocyanin, but their growth was significantly affected because it's high energy. Plants were only trying to protect them by biosynthesizing those pigments, but the growth got affected. So that was not good for us. So we had to come up with an answer. And so what we did eventually was what we call variable lighting strategy. So we give the plants with a lot of red light in the initial vegetative growth phase, so they grow big because the red light helps in vegetative growth. And then when we are trying to when we come to that finishing stages, let's take leafy greens and hydroponics. Okay, usually we grow crops for 4 weeks. That's it. By the 4th week, we harvest the leafy greens. Okay, so we used to grow these leafy greens for 3 weeks in a light that's got a lot of red light, so they grow big very quickly. And then once we got the size we wanted, then we give them a lot of blue light. And when we do so, then their growth is there, and then we also see an increase in just that last week is sufficient. That last week of production showed a significant increase, 10-15% increase in beta carotene and anthocyanins. So kind of like super lettuce, right? Super leafy greens, more nutritional quality. And when we do something like that, people like it. People like to pay more if what they're getting has a value, right? So that's one way to actually also increase profits in greenhouse production. So that was another research we did. The other research we did with light quality was photo sterilization. Okay, so some of these leafy greens, they get infected with bacteria, and it's a very common thing. E. coli, Listeria, Salmonella, these are the different types of bacteria. These bacteria, they don't do anything to plants. They are not pathogenic for plants, but they cause problems to us when we eat them. In the United States, salads are eaten raw, fresh, right? You don't cook them. You just chop them and then you eat them, right? So when you cook, maybe most of the bacteria is dead when you sterilize it. But there we eat salads, fresh foods, so the bacteria are right there, and then when you eat them, they cause sickness in us. Uh, Even you wash it, the bacteria won't completely go away. Okay, that's something we saw, especially bacteria like E. coli. They anchor on the leaves, so you may wash it 2-3 times. The general recommendation is in greenhouses they don't want growers to wash, because if you wash more times and put them inside a packet, then you create a humid environment, so the bacteria will grow during transportation. So the growers don't wash a lot. You are required to wash when you're cooking them or when you're making salads. Even you wash, the bacteria won't get away easily. They're anchored to the leaves. So how do you get rid of them? So we thought of using UV light, and we want to really use not UVA but UVC, which is even more dangerous. It can photosterilize. It can also cause skin cancers on us if we get exposed to it. So we want to be very careful. We wanted to give that UVC at night time, when there is nobody in the greenhouse or when there's nobody's working on an automated basis. So light comes on sometime and then goes away. We found out that we could just give for 2 minutes each day, just for 2 minutes. Okay, at night time when it's dark, there is nobody in the greenhouse. The problem with the UV is, think about the visible light. What is the wavelength for visible light? 400, 700, right? What does visible means?
That was
Visible to us. Where is UV?
below.
It is not visible. So you may turn on the UV light, but you won't see the light. It is there, but you won't see it. So people can simply think that, oh, it's turned off and they go in there, but they are standing right below the UV. You can't see it. It's like your remote. You know, I don't know where that I left the remote, somewhere here, but the remote is sending the light that you can't see. But you have an infrared, sort of like a filter. You can see that there is a red color, light there. You can test it in your homes. So that's the problem with UV light. But we were very careful. We put boards and everything so people don't go inside. At that time, it was right in the middle of the night when there's nobody. And then we did for 15 seconds, we did for 2 minutes, we did for 30 minutes. 30 minutes was killing the plants, too much. But just for 2 minutes when we did that, we saw that E. coli, we inoculated the plants with E. coli, but the UVC plus little bit of UVA kind of photosterilized the bacteria. So that's another research, beyond just the, growth, you can see the benefits of light quality on nutritional quality and also food safety, right? You can get rid of bacteria with this light. So light has got potential values, especially you can try all those things. Some people say, I don't want any yield, I'm growing my plants in my house, but I want them to be really nutritious. How can I increase nutritive value? Maybe they can use more blue light, okay? If you are producing seedlings, let's say you're producing tiny seedlings, you're a flower grower, okay? You're producing petunias, marigolds, those tiny annual seedlings. You want to make sure that the seedlings are small and compact, okay? You don't want the seedlings to be tall when you are shipping them. If the seedlings are tall, they don't look nice, they fall down, they break. So generally, the seedling producers, they make, when they ship them, when the seedlings in trays, the seedlings very compact and short. That's the best size for them. And in order to get that compactness, you can use blue light. You can hit the seedlings with a lot of blue light and they become short and compact. So you can ship them nice and easy. When they get transplanted, they'll be naturally in natural environment and they grow well. But at least during the seedling phase, you can make them compact by just exposing them to blue light. You have a question? Yeah.
So can the effects of the blue light can be completely reversed when they are exposed to the
Exactly.
normal light?
Within a span of 4 or 5 days. Yeah. The plants will completely revert. So there are potential ways, and we also know that, and this is unproven completely. The research, we did a little bit of research, but we didn't get to the point where we can have a conclusive evidence. But there was an interesting observation that we were actually able to repel some of the insects with a specific light quality. Okay, some of the aphids we saw, they were actually reflecting when the light was too bright. So there are multiple ways you can use light quality in addition to plant growth and flowering we talked this morning, right? There are multiple ways you can do that. You can use the light. There is actually been an interesting research I want to bring up to you, especially in greenhouses and also in vertical farms. It is recommended now to add a little bit of far red light. Okay, I said 400 to 700 nanometers for plants, right? But there is also now research showing that a little bit of addition of far red light is going to be useful. And I'll explain why that is. When you grow plants under far red light, you will see some morphological differences in plants. Okay? Their structure and shape changes. One of the main things you will notice is that the plants exposed to far red light, their leaves are wider. There will be fewer number of leaves. Normally grown plants may have 40 leaves on that, but the plant exposed to far red light will have smaller number of leaves, but wider leaves. Okay, it's a shade avoidance mechanism. Okay, that's what we call shade avoidance mechanism. All those tropical plants you buy, monstera, philodendrons, dieffenbachias, we put in indoor plants in our houses. Notice their leaves. Their leaves are wide and big. The reason why they are wide and big is they are trying to intercept every photon falling on them. They grow under the shade. Under big tall trees in tropical forests, they are under canopy plants. They don't get a lot of light, so they have to capture every photon. And so one way to capture every photon is to make their leaves wider. That's why they are wider. The same thing, that's called shade avoidance. They are grown in shade and they come up with a mechanism, right? The same thing you can replicate in plants artificially by exposing them to a little bit of far red light. The reason why we want to do that is, the recommendation is that you give these plants, any small plants, initially for the first 1 or 2 weeks, a little bit of far red light. When you do that, their leaves start to expand. And when the leaves expand, they intercept more light than the normally grown plants. And when they intercept more light, they start growing bigger and then turn off the far red light. You have LED fixtures nowadays where you can turn on a specific quality of light. So the recommendation is that, turn on those far red lights just for a week or so. The seedlings really have wider leaves. They start intercepting a lot more light and then turn it off so they grow faster. So there is something like that going on, but there are many ways you can play with light composition, not just for photosynthesis. I gave you examples of nutritional quality, food safety, shade avoidance syndromes, like situations. All those are very, very important. Okay. Any other question on light composition, light quality, flowering, anything that comes across your mind? Anyone interested in becoming a greenhouse researcher, grower, or want to start a business in the future? Is anybody in this group interested in greenhouse? You want to do a greenhouse thing? Okay. What crops do you want to grow?
I'm thinking of blueberries.
Blueberries. Okay. Okay. Um, is it a big crop here, blueberries?
Not big crops, are super food.
Yeah, it is enriched with anthocyanins, right? It's very healthy. By the way, blueberries are consumed a lot in the Scandinavian countries, Denmark, Sweden, Norway. They consume a lot of blueberries, and they relate their blueberry consumption to long lifespan, because blueberries have got a lot of anthocyanins. But there are specific varieties of blueberries that are highly suitable for a greenhouse or even a vertical farm nowadays. Yeah, yeah, that's good. Yeah, and where are you from? From here. Okay, and then you want to grow them in a greenhouse.
Greenhouse are probably in the mountain regions. I have land in mountains. That's why I'm thinking of.
Yeah, you bring up a point. So we'll talk more about when you talk about greenhouse designs. But when you get to the mountain regions, you want to have a really rigid structure, because wind velocities is going to be pretty high. It's going to blow over your greenhouse. But we'll talk about that when we talk about greenhouse designs. Okay. I'm not aware of any research related to blueberries and light composition. A friend of mine did some research on pollination aspects with bumblebees and honeybees. But there may be research that I'm not aware of. People have used light composition to alter the nutritional quality. I know that in tomato production, they do change light quality during fruiting phase in order to increase fruit size and pigment composition, lycopene content in tomatoes. The lycopene is a pigment inside tomatoes. In order to increase the lycopene, there is some Dutch research that shows that if you expose the fruit to more red light, you get a lot of lycopene. So think of a tomato plant. It's a vine, right? What we call high wire tomatoes. These are not your standard tomatoes like a bushy type tomatoes. These are what we call indeterminate tomatoes. Okay, and you grow them, you hang them to the roof. It is using a string. So you probably take 2 wires, right? Now, how do you expose? So the fruits are coming here. Sometimes the fruits are up there, up down here, right? At different heights. Now, how do you expose those fruits to a specific light? If you put lights up there, the plant may completely shade, the leaves are so big, the fruit may not be receiving that exact light. So that's why in tomato production, what we do is we don't put the lights at the top. Okay, we put the light along what we call intra-canopy lighting. So these LED bars, they run like this, where the fruit is there, and these LED bars can be taken up or down, where the fruit is, intra-canopy lighting. And this is what the Dutch greenhouses are doing, and what they are trying to do is they increase the amount of red light during that fruiting phase to increase the quality. So that is something I've seen, and they're showing that it is feasible. Okay, so there are many ways you can modify plant growth, yields, nutrition quality, modify food safety by tweaking the light quality that you're providing to plants. It's a very important fundamental cardinal factor. Okay, knowing that information helps you now to think about how can I change this, how can I do this, right? So keep in mind, we'll talk more about LED lights tomorrow, but that is an evolving technology. LED lighting is an evolving technology. Every day, the prices are being slashed down. The LED lights are becoming less and less expensive and more efficient. They're going to really, be really useful in making this whole greenhouse production more sustainable in the future. Yeah. Any questions on light composition so far? I don't know how much time we have. We're pretty close.
Production, tomato plant in per plant production.
It varies by variety, season, location. We have to check, but I would recommend you look into some of the Canadian greenhouses where they actually get the highest yields. Well, I would take back. Actually, the Dutch greenhouses have higher yields. Canada is slightly, if I'm not mistaken, the yields are slightly lower. You said you get about 15 kilograms per plant?
12 to 15 kilogram per plant.
And how many flushes? How many? It's like 1 year crop, or is it like 6 months?
6 months.
Yeah, do you do 2 crops? Okay, and then that's about 15 kilograms per plant per 6-month period. Yeah, I mean you're there, but there may be an opportunity to increase. And I again, it depends on the variety. It's highly dependent on variety and the cultural practices.
The hydroponic variety is not available.
So do you use beefsteak tomatoes?
Beefsteak tomatoes is very
Yeah, big ones. Are you using Roma tomatoes? What is the variety that you're growing?
I think we are using variety Alka Rakshak variety is probably.
Is that a Roma tomato? Is a small one?
A small one.
Yeah,
Aroma,
yeah,
right.
a Roma one. Yeah, their yields are slightly lower, but again,
Like I will use beefsteak tomato.
but people don't like it here, isn't it? Yeah.
They use it for
If you get 1 kilogram, one tomato, people don't like it. I want more tomatoes in 1 kilogram, right? That's what it is. But beefsteak tomatoes are more for burgers.
burgers in India usually.
Yeah. But in any case, it's 5 p.m. Okay, so a couple of things. Be there on time tomorrow. We'll start at 9:30. Okay, and if you know somebody who missed this afternoon, do tell them. By remaining absent, they're not going to gain anything. They paid for it. They're losing their money. Okay, just tell them, because we're going to go such a fast pace. If they miss classes, they can't catch up. I will repeat that again tomorrow morning. But I hope you all come back. I hope that this is interesting to you, and we'll learn more. Okay. All right. Very good. Very good. You're most welcome. And for all of you, if you find something really a great location, and Dr. Singh was asking me, if you find something that is really beautiful, let me know. I'm trying to visit Uttarakhand while I'm here, so I'll be more than happy to get that information from you. Okay, first-hand information.